We talked about bosonization, and as you remember, if we looked at a boson whose action was 1 by 8 pi del h square, and we looked at the usual, what was it, 2 pi, 4 pi, I can't remember, psi bar del psi, maybe 2 pi. There was a sense in which these two theories were the same, at least the chiral algebras were the same. Okay, and the map was that psi was equal to e to the power h, psi bar was equal to e to the power minus h. Okay, now to start this lecture, you know, this business about the chiral algebras being the same, it's a very abstract thing. It's a kind of thing, I mean, it's very nice, but it's very abstract. And you might, but it would be more satisfying if there was actually an equivalence between two theories. Okay, so and actually that is the case. The cleaner statement about bosonization is that the cleaner statement about bosonization is that is a relationship between a particular bosonic theory and the standard free Fermi theory in a way that is sort of quite illuminating. Okay, so I'm going to take the first half an hour, 40 minutes of this lecture to explain that, to make these ideas more concrete. Okay. In order to do that, we're going to need a diversion. The diversion is we're going to need to study free bosons with target space periodically identified. Okay, so this is something we're going to have to do anyway for various things in string theory. It's a good opportunity to start that discussion. So consider, I'm going to work once again in our space-time normalization. So 1 by 4 pi alpha prime del x, the whole thing square. And this is our action. And suppose we had this, suppose we had our field x to be was identified with x plus 2 pi r. Suppose this was the case.
For each of the dimensions.
For let's take one x for now. If there were many dimensions, we might make more complicated identifications.
So this is just one x.
One x at the moment. If there were many x's, we could make more complicated identifications. It could be a lattice of identifications. Okay. This is also something we'll consider at some point, maybe even today, depending on how the lecture goes. Okay, but at the moment, let's just take one x. Okay. Now, suppose we want to do this the quantization of this theory. Okay, so let's go back to the cylinder. We have x as a function of sigma and tau, and in this theory on the cylinder, we can ask, what is the difference? What difference does it make that x was periodically identified? Last semester we thoroughly studied the theory where x was free, there was no identifications. What change does it make?
It will be quantized.
Excellent. So one point, if you remember what we did was we took x and we expanded it at any given time as x naught plus p times tau plus sum over n alpha n by n e to the power I n sigma. Okay, yeah, let's do it fully. So sigma plus tau plus n alpha bar n by n e to the power I n sigma minus sigma plus tau. I hope I've got the I hope I've got the right signs here, which I never remember. I hope I got these signs right. Not that we're going to say anything about it. Maybe we should be putting an overall minus. Let's remember, in a harmonic oscillator, it goes like a e to the power minus I omega t, right? Or is it plus? This is the thing I'm trying to remember. We should be able to figure it out because states go like e to the power minus I omega t, and the way states are e to the power minus I omega t, and suppose we had a dagger on 0.
So states go e to the I omega t, e to the minus I omega t is Schrodinger picture.
Right.
So if we are in Heisenberg picture, then if we write the field operator as a e to the minus I omega t, then field operator dagger will go like plus I omega t. So if we make them time independent, the states will go like minus I omega t.
Well, right. What I was thinking was I'm going to take a state which is this. Yeah. Okay. How about just looking at the state which is obtained by x on 0? Okay. The state which is obtained at x on 0 yeah, but this is the Heisenberg picture.
So there is a conversion between Heisenberg and Schrodinger that is changes the sign.
Yeah. This is always very confusing, but I will accept this if you feel you're sure you're right. Okay, good. Then positive n is should be like a, and so I've got these wrong, right? So negative n will go like this. Right. So we took this we took this thing and we did an expansion of this sort. Okay. Let us also remember what the right factor of alpha prime behind this p was. The right factor of alpha prime behind this p was obtained as follows. We wanted this to be the momentum conjugate to x. So let's keep only the 0 mode part. So we get 1 by 2 alpha prime x dot square as the Lagrangian. So the momentum conjugate is equal to x dot by alpha prime. And therefore, if we put an alpha prime here, x is equal to p alpha prime t tau. So that looks okay. Okay, so we had this kind of expansion. And one of the things that Upmanyu pointed out was that previously p was an arbitrary real number. Okay, but because the commutation relationship between p and x naught, and because p is conjugate to x naught, and because x naught is periodic with 2 pi r x naught, in the usual way, p has to be n divided by r. That's because a wave function behaves like e to the pi p x. And the wave function has to be well defined. Under x goes to x plus 2 pi r.
N over? Okay, yeah. Correct. N over r.
Right. Under x goes to x plus 2 pi r.
Yes.
And that will work if p is n by r. So there's one difference. This is the difference that we would have had we been dealing not with a theory of strings, but a theory of particles. If you take a particle and send it propagating on a space which has periodically identified space, its wave functions would also have to be well defined. So all its momenta would always be n by r. This is familiar. Now you can ask, is there any further difference?
Number of windings of the string.
Excellent. Exactly. The second difference is that this is not the most general expansion anymore. Okay? Right. Because we can have topologically inequivalent sectors of solutions. Solutions in which the string, as sigma goes from 0 to 2 pi, that the string winds around the space-time circle n times. Okay? Suppose we are in a sector in which the string winds around the space-time circle n times. Can we find a solution of the string equations of motion that does that? Very simple. Because the solution to the equations of motion from here are del squared x equals 0, x being linear in coordinates is a solution. So choose x being linear in sigma. Okay? And if you want to wind n times, you want x is equal to n sigma divided by r times r. So that when sigma increases by 2 pi, this increases by 2 pi n r. Okay? So, if we want a solution in the nth sector, I'm going to put an n here. Okay? I should have x naught plus n sigma r plus alpha prime PR, p tau, plus this sum here. Okay? Now you could ask, well, how do you know that this sum is unaffected by this winding business? And that's simply because, that works simply because suppose we say this plus x tilde, then the action for x tilde is the same as the action for x, because the action was quadratic and this was a solution to the equations of motion. So there are no cross terms. Okay? So the expansion of the remaining part after we've done this n sigma r behaves exactly like the expansion for an for an unwinding string. This part of it, the oscillator part, just doesn't know about the fact that the string, that x naught was periodic. Okay?
So winding affects only the zero mode sector.
It affects only the zero mode sector. Exactly. Okay? So, in the situation where you've got this periodic circle in space-time, okay, we've got these different sectors of winding number n, and sectors of momentum p. Note that this is discrete, and note that p has also now become discrete. Let's call this w. Let's call this w so we don't mix up with this n. Okay? So instead of having one continuous number in the zero mode sector, we've now got two discrete numbers in the zero mode sector. Now, at some point in our analysis of of the string, we broke up this thing into a left moving and a right moving part. Got it?
Winding is because x is identified.
Sorry?
Winding number
Hmm?
is because capital X is identified with capital X plus winding number times r, and discreteness of p is due to
The fact that wave functions for x naught have to be well behaved. X naught is identified with x naught plus 2 pi r. That only works if p is equal to integer number by r. The wave function has to be single valued.
And this xn will be denoted by xw.
Thank you.
The identity is for them.
For w. Perfect.
What is the canonical conjugate of w?
What is the canonical conjugate of w? Well, w is a number. I mean,
It's not an operator.
w as written is not an operator. What one can do is look at this as a subsector in an enlarged theory, and then your question will make will be more meaningful. Hang on for a minute. We're going towards that. Okay.
this, right? We have a cylinder, and then we have. Suppose we're just thinking about the one X field, the one which we compacted, right?
Yes.
And so essentially, it has like an S1 kind of attached at each point, right? Its fiber is sort of like S1 everywhere because it's compacted, right? And then, so you sort of have the kind of thing that's going on is that when you get around, you know that you have to be at the same point of the S1 that you may have gone many times around.
Yes.
What are the other modes?
This?
So I guess that would sort of be, that's sort of just saying if you go to momentum space and your whatever your space is compactified and momentum space is periodic.
Exactly.
What are the other modes?
It's discrete.
Right? The
Yeah.
non-zero sector.
What are these modes?
Yeah.
Well,
They're just like
the vibrations.
vibrations around the circle.
As the string is wrapped,
Right.
but it's also vibrating. So you see, we haven't. This is just conformal field theory.
Right.
We haven't done diffeomorphism or anything like that. So this can vibrate in every direction, including the direction of x. Okay. So I've got these different points on the string, and then they're moving like this.
Okay. Does this make sense? Because maybe what I'm struggling with is because I'm imagining mapping a cylinder to a circle.
Which is your cylinder? That's the world sheet.
The world sheet and mapping it into.
Remember that this is time.
Yeah.
So at any given point of time, you've got a map of a circle to a circle.
It's a circle.
Okay.
So those are classified by the first integer n or omega, whichever one you want to think about.
Exactly. So topologically, it's a circle to a circle.
Right.
But what you could have, imagine a rubber band.
Yeah.
Imagine a rubber band wrapping a pole.
Yeah.
Okay, a groove on a pole, so it's not moving up and down. Okay. First, you could wrap it m times.
Yes.
But then once you've wrapped it, you can also set it vibrating.
So that's the omega and the p.
No,
The n and the p.
that's these.
Okay.
This is the wrapping.
Yeah.
This is if you set it moving.
Okay. Okay. Yeah.
Okay? And these are the vibrations. Is this clear? Okay, the compression waves around the rubber band. Okay? Right, fine. Remember, at the moment we're just in conformal field theory. In full string theory, only some of these oscillators will be physical. Exactly, they're pure gauge. But we're not seeing all that at the moment. We're in the picture where 26 oscillators are all physical. We've not yet removed it. Okay, excellent. So now, one of the things that we like to do was to write this as a sum of a left moving part and a right moving part. Okay, so let me remind you how we did it last time. Well, clearly, this was by itself right moving. This was by itself left moving. And when we didn't have this additional complication, what we did was we broke this up. What we did was we wrote this as alpha prime PL by 2. We wrote this as alpha prime P by 2 times tau plus sigma plus alpha prime P by 2 tau minus sigma. Okay, we were doing nothing because the sigma cancelled. And then we sometimes called this quantity PL and this quantity PR. Oh, and anyway, we grouped this into the left moving part and this into the right moving part. Okay, so we wrote x is equal to x0 plus xl plus xr. And xl, for instance, the left moving part, so tau plus sigma, was equal to alpha prime p by 2 tau plus sigma plus this part, which I'm not writing again. Similarly for xr. Okay, let's do the same thing. Only this time we have this extra sigma dependence. Okay, so we want to do the same thing. We'll just write, so what will we do we'll write sigma plus, let's say tau plus sigma. Tau plus sigma, let's call this sigma plus.
PL minus PR will be proportional to W.
Correct. Tau minus sigma is sigma minus, or equivalently, tau is equal to sigma plus 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 sigma minus divided by 2, and sigma is equal to sigma plus plus sigma minus, so minus sigma minus divided by 2. And we just plug these in and collect powers of sigma plus and sigma minus. Okay. So we're collecting the powers of sigma plus and sigma minus. So what will we get? We'll get xw is equal to x naught plus, now let's see, the sigma plus part will be plus tau plus sigma, that's sigma plus, by 2 into, from tau we get an alpha prime, and p was n by r. Okay, from sigma we get a plus wr plus tau minus sigma divided by 2 into, once again we get, from tau we get alpha prime n by r plus, and now we'll get a minus wr. Okay. Now, let us continue to follow the convention. Let me get the factors of 2 right for our conventions. Alpha prime by 2 PL times log z. Log z is this presumably. Yeah. So let us call whatever's here PL. That was, I think, our convention last time. No, but with an alpha prime. So we'll take the alpha prime out. Okay? And so now once again we can do the expansion that we wrote down up here. So now I'm going to rewrite that expansion, but just in the 0 mode part. Because everything interesting is happening in the 0 mode part. Everything new is happening in the 0 mode part. Okay? The expansion is x is equal to alpha prime pl by 2 into tau minus tau plus sigma plus alpha prime pr by 2 into tau plus sigma, tau minus sigma, where now we have PL is equal to n divided by r plus omega r by alpha prime, and PR is equal to n divided by r minus omega r divided by alpha prime. Now the next question that we can ask is, in this theory, what are our vertex operators? In the free boson theory, we knew, I mean, without this periodic identification, we knew the answer. The vertex operators were just e to the pi k dot x or del x, and many derivatives on x. All the many derivatives on x are the operators dual to the oscillators. They are totally unaffected.
So clearly you can have PL and PR instead of K.
exactly, exactly. So, what?
You can have PLX and then del X kind of things.
So what you can have, here what we had was K into XL plus XR. Right? And that came from the fact that PL was equal to PR in what we had last time. Okay? So what this is going to generalize to is e to the power I PLXL, okay, times e to the power I PRXR. Where PL and PR are given by this, and I hope I've got my factors of 2 right. Just 1 minute. Just 1 minute. Yeah, I think I've got the factors of 2 right. So e to the power I PLXL times e to the power I PRXR. This is the natural generalization of that, because PL was the left momentum, the momentum conjugate to tau, to this quantity, and PR was the right momentum. I mean, the PL is the part that is purely left moving, PR is the part that is purely right moving. Okay? So, the vertex operators in our theory, perhaps the main point of this little interlude in today's lecture is to show you a place where the kind of thing we were talking about yesterday, namely separating the e to the power IH from the e to the power I H bar. You remember one of the main points yesterday was we were dealing with the left moving sector of the boson separately from the right moving sector. Okay? That logic would appear to indicate that we could take an e to the power I KL HL and an e to the power I KR HR, not necessarily with KL not necessarily equal to KR. In the one theory we looked at before, namely just the free boson, that never actually happened in the theory. We had e to the power I kx or e to the power I kh. Okay? Now I'm trying to show you a context where you can do such a separation. However, this separation is not completely arbitrary.
Because PL plus PR has to be sort of an integral.
Because PL and PR are determined, I mean, by the same 2 integers.
So there are constants about it.
There are constraints between them. Okay? Now, I want to show you that these constraints are precisely what would lead to good things. Okay? So the first way we're going to see this is as follows. Suppose I take, you might remember that in yesterday's lecture I was complaining if you did some separation like this and you were completely free, you would give rise to operators that are mutually non-local to each other. Right? Because the phase that you would get by taking one guy around the other from this left moving part would not in general be compensated from the phase you would get from the right moving part. Now let's check whether that happens or not in this situation. Is this clear? Is the question clear? Okay. So, perfect. Okay, so what I'm going to do is to take one such operator and take it, what I'm going to do is to take the OP of one such operator with another such operator.
Sorry, just to be sure.
Yes.
These are like function of J
This is function of z. Let's say this is a function of z bar.
This is like H and H bar from yesterday's
Exactly.
discussion.
H and H bar. Yes, exactly.
H and H bar.
Exactly. This would be like H, and this would be like H bar. Left moving and right moving part. Yeah.
Previously that made PR to be 0.
Yeah. If we made PRs, previously we took some very particular number here and let PR be 0 in what we were doing yesterday. Okay? And we're going to be heading towards that. But right now, let me just look at this completely abstractly. Okay? So I've got this kind of vertex operator here. And so suppose I have the operator number 1. Let's call it V1.
But H was real yesterday.
X is also real. We're just separating into left and right moving part. Maybe I shouldn't have said H and H bar. H left and H right.
Yeah, this is on the cylinder. And
H
what we are
analytic,
doing-
H anti-analytic.
No,
Sorry.
this is on the cylinder, and what we were doing yesterday was on the plane.
Uh-huh.
In the H and H bar.
Yeah, sorry.
No, no.
But we're always just separating in left moving and right moving. That's
no,
it.
yeah, this is.
Yeah.
No, I mean with regard to his question.
What was that? Yeah. I'm not sure I understood the question,
Okay,
but if you guys are all happy. Okay.
No, yeah,
Yeah.
this is perfectly clear. Yeah.
Okay. Okay. So now suppose we've got a V operator like this. What I want to do is to take the OP of V1 and V2. That gives whatever. You know, the singularity in the OP is going to give you the phase as one operator goes around the other. So what I'm going to compute is the singularity that appears in the OP. Okay, so as we saw very much yesterday, we're going to get some number times the normal ordered product of V1 and V2. So suppose we took V1, I should have said. So V1 is such an operator with N1 and W1. And V2 is another such operator with N2 and W2. N1, N2, W1, W2 are arbitrary integers. Okay? So what will we get? Well, we worked it out yesterday, right? We get Z to the power, except we worked it out on different conventions. So we'll, let's get our conventions back. Z to the, in yesterday's conventions, it was P dot P.
Yes.
So we'll get PL1 dot PL, PL2. But now we have to put back our alpha primes. So we'll get an extra factor of alpha prime by 2. Right? So that if you set alpha prime equals 2, it goes back to what we had yesterday. And we will get Z bar to the power alpha prime by 2 PR1 dot PR2. Why only one alpha prime? Because the factor came from the 2-point function. And the 2-point function had a minus alpha prime by 2. Right? I mean, the fact, the thing in the exponent was the 2-point function. The 2-point function is one factor of alpha prime. Okay? Now, what we want to know is whether as we go, take one point around to the other, come back to whether it's single valued or not. So that's a question of what happens because of the phase. The danger is the phase, right?
Yes.
Difference between PL and PR probably integer or something that is.
Right. This guy picks up the phase 2 pi I times this quantity. This guy picks up the phase e to the power minus 2 pi I times that quantity. Okay? So the net phase that you pick up when you take one guy around the other is e to the power 2 pi I into alpha prime by 2 PL1 dot PL2 minus PR1 dot PR2. Is this clear?
The momentum modes would cancel and only the winding would remain.
Well,
Hopefully.
let's just calculate it. Okay, let's just do the calculation. So
The cross terms would remain.
it's only the cross terms that will
Just the
remain.
cross terms would remain and the alpha prime will cancel and
Yeah, so exactly. So exactly, the right and the left differ only because by the sign here. So anything quadratic in, let's say, left has this thing here squared, this thing squared, will cancel between PL, the PL.PL and PR.PR. Okay, what remains only is the cross terms. In the cross terms, R cancels out. Alpha prime cancels out because of this quantity, and 2 cancels out because the 2 comes with the cross term comes with a 2. That cancels this half. Okay, and then there will be an additional 2 because there's a minus with this. So we will get 2n omega.
So where's the other 2 from? One of them is coming because the minus gives you the 2.
And the other term is coming.
I think
That's the only 2, maybe I said.
Because you have, it's not,
yeah, I think there's only one here.
Yeah, you're right. You get e to the power 2 pi I, and one term would be
N omega. N W.
n1 omega 2
Oh yeah, sorry. Oh yes. N1
minus, no, plus n2 w1. Yeah, that was what I was calling 2. Sorry, yes. Do you see? So it's perfectly an integer. It's perfectly well defined. So you see, this is the thing. You can separate the left and the right moving parts and land on your feet. Namely, get operators that are give you whose correlation functions are mutually local, mutually well defined. Okay, all well defined, provided you do things properly.
This technically implies there's possible allowances for a weaker condition.
Yes.
Namely, that's sort of the product of these, like, if I demanded that the n's be an integer and the omegas be 1 over
and something.
yeah, find something like,
Yeah.
it might be a weaker condition than strictly n and the omega being.
If
Yeah.
they are integers, then this is certainly good.
Excellent. You know, precisely in a more complicated context, this was precisely the question asked by Narayan. Narayan asked the question, if I've got n free bosons and I don't know how to get it, but I will just try to make the most general identification, the most general set of PLs and PLs that are allowed. Clearly, they have to form a lattice because the OP will generate. If you have P1 and P2, you'll generate P1 plus P2. So clearly, it has to form a lattice. So what is the most general structure that is allowed that gives everything nice and consistent? One of the demands he made was that it was mutually self-local. Okay, there was one more condition that he imposed, namely that the partition function of his theory would be modular invariant. We'll come back to that very soon. Okay.
Won't that be a consequence of starting from a conformal? If I start from a conformal field theory, don't I sort of?
If you started from a well-defined conformal field theory, you would. But now what we're doing is,
But he's sort of taking a step back.
yeah, you know, he's just making an arbitrary identification. Right? He's saying, let me say that. So his abstract point of view was the set of possible PLs and PRs because of the OP necessarily form a lattice. Now, let me not ask where geometrically it comes from. Like, we got a nice lattice by putting the theory on a circle. Because that was such a nice thing to do, we were pretty sure we'll land on our feet. Because he started with a physically well-defined situation. Narayan's point of view was, forget physics for a moment. Oh, you know, I mean, forget this kind of physics for a moment. Yeah. Let me just allow any possible lattice of allowed PLs and PRs. And if the final theory I get obeys all consistency requirements, I'll be happy. Okay? Actually, if you take Narayan's construction with one free boson and free fermion, he found the most general solution. And it is this. It is. Okay? But he did more. He found the most general solution with D free bosons. And he thought he found more. He found more than what you could do by putting the D free bosons on a
D different circle.
yeah, even on a angular circle, you know. If you just choose a torus in D-dimensional space, that torus could have angles. Yeah. You could put an arbitrary identification, not necessarily rectangular, in this D-dimensional space. He got more than that. One way of measuring how many parameters you would get from these tori would be effectively it's the number of symmetric, it's the number of components in the metric in D dimensions. Because all tori are like this in the right metric.
Yes.
So you can trade this for the constant components of a metric. Constant components of a metric are D into D plus 1 by 2. Narayan found D squared parameter worth of solutions. And that sounded, you know, this, by the way, this D into D plus 1 by 2 and D equals 1 is 1. And that parameter is our R. Okay? But in 2 dimensions, this would give us 3. And that parameter would be this first R, the second R, and the angle. Okay? This is what you would naively get geometrically. Narayan got more. He got D square. And then Narayan, Samadhi, and Witten found that actually even that more you can interpret from physics. Okay? Which is this. I may even tell you about it. Okay, let me just say it here because I'm not sure we'll get to it this lecture. But since you've asked the question. You know, in the sigma model for free bosons, there's the metric, but you can also add the B field. Yes. Epsilon AB. B mu nu del A x mu. Del A x mu del B x mu. This is one of the standard deformation terms of the string theory, world sheet action. Okay, this is, I haven't yet told you about that, but this is, you know, there's a generalization of everything being done in string theory from moving away from flat space. We've only dealt with string theory in flat space. But you can look at string theory in arbitrary backgrounds that solve Einstein's equations. There's a very simple background that solves Einstein's equations, namely B mu nu. You remember the two-form field?
Yeah,
Karl-Bromon field. B mu nu equals constant. This solves Einstein's equations because the action, string theory action only, I mean, all equations of motion only know about the field strength of B mu nu. So B mu nu equals constant is, you might think, just pure gauge. And it would be pure gauge.
in non-compact.
Exactly, except that we've got compact spaces. So just like if you've got a constant gauge field on a circle, that is not pure gauge. The Wilson line is gauge invariant. In the same way, the Wilson surface, B mu nu integrated over a non-compact, over a compact torus, is gauge invariant. Okay? So adding such a B mu nu is clearly a solution to the equations of motion because it's pure gauge, only it's not pure gauge. It solves the equations because H is 0. But it changes the physics. And we may go through it today, or we definitely go through it soon. The change in the physics, how many different parameters are there? Well, the number of parameters in B mu nu, which is d into d minus 1 by 2. Add them to that, you get d square. And those were the additional parameters that Narayan found compatible. So I said all this just to say that what you suggested has been tried, it doesn't work. Okay. Yes.
So I should think about this as psi and psi bar and choosing different vacuum for psi and psi bar.
What is psi and what is psi bar?
From yesterday's identification,
Ah.
we had psi and psi bar, and this constitutes.
No. We should be careful. Psi and psi bar were both left moving. We had two fermions, and we were looking at both of them were left moving fermions.
Psi and psi bar were e to the plus h and minus I plus h and minus I.
It is choice of vacuum for left moving and right moving parts.
Yeah. See, yes, in yesterday's lecture, everything we were talking about was left moving,
Yes.
both on the bosonic side and the fermionic side. Here I'm bringing back the right moving sector. So if we want to do some sort of fermionization,
Yes.
we will need also a right moving fermion.
And then you can choose different vacuum for them.
Different vacuum. At the moment I'm not committing whether it's a vacuum or not.
You are not committing, but sort of this implication that with this particular kind of choice, you can make consistent OPE.
Yes. There will be at the moment we're just talking about the spectrum of this free boson theory.
But since these are well defined,
Yes.
so if you had this right moving fermion, left moving fermion,
Yes.
you could have chosen different vacuum provided they satisfy this constant.
Exactly. So there is a particular combination of sectors of the fermions. This I will try to explain, but this will map to some choice of Raymond and Nebuchadnezzar sectors in the fermion theory when we actually look at the bosonization. And there will be, it will tell us that there is a combination of Nebuchadnezzar and Raymond sectors of the fermion that are mutually local.
With this constant, yes.
With exactly chosen in this way. Okay? So you see that what I wanted to say at this point was that we started with very simple physics, namely just that the space-time circle was compact. Okay? And we've already got quite interesting vertex operator structures. You know, some non-trivial combination between left and right that sort of looks like it's about like it might work.
So that would correspond to type 1 string theory?
No.
No, I mean,
At the moment,
no, in terms of the particular combination of the Nebuchadnezzar and
no, that combination is what people call type 0 theory.
I see.
Yeah, it's a modular diagonal invariant, very simple thing. Diagonal modular invariant. Sorry. What? Yeah. Okay.
Yeah, we ignored all the z-bars yesterday.
We ignored z-bars completely. Today we're bringing it back in, so that we can deal with the whole theory. Okay. Other questions or comments?
What is your comment? You had some comment yesterday. Even if you make nu and nu bar, or you took z and z bar and then mod, they were fine. Okay.
If you made them equal.
Equal. Now you are making them different.
Now I'm making them different, right? And still it's okay. That's what's non-trivial. If you made them equal, it's obviously okay, right? Because
Z bar, z bar.
this will cancel this.
Z
Yes.
bar.
Yeah. Yeah. Okay. Excellent. So maybe we'll go through the one additional thing, since we've gone through this so nicely. One additional consistency check along these lines. Maybe I should just finish this discussion since we're going to need it anyway. Fine. Let's just go. Okay. So let's go through the. Thank you. One additional consistency check along these lines, and the additional consistency check is that of modular invariance. Okay. So I want to check whether this.
But you still didn't answer. What is the commutation relation between W and X0?
Well, at the moment No, W is a number.
So n is also a number.
N is also a number.
Commutation relation between x0 and p, you made this p to be n by r. So
Well,
non-trivial commutation.
Well, fine. You know what you can do is this. You can write XL is equal to X0 plus PL alpha prime by 2 plus X osc and XL0. And then we have XR is equal to X0R plus alpha prime PR by 2 plus XR oscillator. You could formally say this, okay? And then you would demand that X0L and PL have ordinary standard commutation relations. X0R, PR, people do this a lot. It's a bit, you know, it's like some bigger Hilbert space. Because there wasn't an X0L and an X0R, right?
Yeah.
Then you would have to take things in that bigger Hilbert space and then view it in the physical sector where there's only one X0. Something like that. You know, one could play such games. Okay, and that is sometimes a useful game to play. To imagine that there was an independent X0L, but then it's for standard commutation relations between X0L and X0R. Okay, but you have to do this with care. You're inventing some structure that wasn't there really in the original theory. Okay, but let's move on. What we want to do here is to try to compute the partition function. To try to compute the partition function of our free boson theory compactified on a circle. Oh, by the way, something I should have said for future use is we wanted this guy to be an integer. Now, let us define this quantity as an inner product on the two-dimensional lattice of possible momenta.
And the calculation we have done, that shows this quantity is an integer.
That shows this quantity is an integer. And now I'm going to give some fancy words to this calculation. Okay, no more calculation, we'll just do words. Okay, okay. Look, suppose I've got a two-dimensional space. One dimension is for left movers, and the other dimension is for right movers. Is momenta for left movers, PLs. Second dimension is momenta for right movers, PRs. On this two-dimensional space, I define an inner product, which is alpha prime by 2, PL, P dot P minus P dot P. It's not positive definite.
Right, it looks like a symplectic form more
Yeah,
than
more like symplectic.
Fine. Okay. But I define this product. You know, ever since Einstein, we've not been scared of defining inner products that are not positive definite. Okay. Okay. So we do this, and then we ask, what is the condition? The condition that we checked that this was an integer. Okay. Well, what was the condition for this inner product? And the condition was that this lattice of momenta were of the form that the inner product of any momentum with any other was an integer.
Root space decomposition. Then if you have fundamental roots and fundamental weights, simple positive roots and fundamental weights, their inner product will be of this form.
That's right. That's right. That's right. And that is an example of a more fundamental notion for lattice. You're using the ideas of group theory. But there's a more elementary notion when you have lattices. Whenever you have a lattice, people define the following quantity. Well, I call it a dual lattice. Okay? Whenever you have a lattice, you define the set of all vectors such that the inner product of any vector of a vector of this new guy with any vector of the old lattice is always an integer.
Yes.
Okay? Such things are called, people who study lattices, at least when their work is quoted in string theory books, they're called dual lattices. Okay? Okay? So what we have seen is this. Since this is an integer for every momentum, it must be that this lattice,
Self-dual.
well, lies within its dual.
Okay, I see.
Can you again describe the definition of the dual?
I'll say it again.
I start off with some lattice.
Yeah, let me give you a lattice L. Okay? Now I take another lattice which I'll call D. D is defined for to obey the following property. Let W belong to D, and let X be any M be any vector in N. Okay? Then the definition of D is that W M is an integer.
Really, I want to start with two lattices and then sort of have a map from sort of their tensor product that's going to look like an inner product, but has the property that it ends up being an integer.
Right. It's, it's routine to, given a vector, it's routine to define a dual vector
Yeah.
such that the inner product
Right.
of that,
So instead of looking for the dual space that's mapping you back to the reals, you want the dual space that maps you.
that's right. Okay? So what we have seen is that this lattice of possible vectors in PL and PR space, okay, has to lie within its own dual. That, if that is the case, then this object here, if that is the case, then this object here is going to be single valued. Is this clear? Now, there is one more condition.
Was the argument and the claim that you said before that they necessarily have to be integers and all that? In other words, they're here. Does this tell you that it's not only contained in this dual, it's equal to the dual?
Yes, if you put all the other conditions,
Yes.
it
For
will.
example, this would be self-dual.
This is self-dual.
Correct.
Okay, it's an even self-dual lattice. Okay, hang on. Let's since we started this, I'll just complete. I hadn't actually planned to, but we'll just complete this today. It's interesting, right? It's interesting. That's in the end what we study physics for. Right? I mean, okay. Okay. Fine. So let's do this all thoroughly. Okay. So now let's put another abstract condition on these guys. The other abstract condition is this. Look, suppose I want my partition function to be modular invariant. This is a condition I'm going to check carefully now in a bit. But before checking it carefully, there's something that is totally obvious, which is this. Remember, we write this q, which is e to the power 2 pi I tau, and q bar, which is e to the power, do people do minus 2 pi I tau bar? And then our partition function is trace q to the power L0, q bar to the power L0 bar.
What's tau bar?
Tau bar, if tau is equal to tau 1 plus I tau 2.
Oh, okay. This is not the same tau from the cylinder.
No, I'm sorry.
Okay,
I'm sorry. I'm sorry. Maybe we haven't. I'm a bit hazy about what we talked about last semester, not. But given a torus,
What's that?
okay, you identify the. I should say, given a torus, okay, a torus can be thought of topologically, and in complex structure-wise, as the following: Z is equal to Z plus 2 pi. This is the first identification. And Z is equal to Z plus 2 pi I tau. Or maybe without the I.
Z going to Z plus 1 and Z going to Z plus tau. So maybe not I. I don't know.
Z goes to Z.
I mean, if tau is real, then the second is.
Yeah, I think 2 pi tau.
Because z going to z plus 1 and z going to z plus tau is a standard identification in which your Q's look like that.
Yeah. Now I put 2 pi's. I think I want my 2 pi's because I want one of my things to be, my torus to be of size 2 pi. Space to be size 2 pi. Yeah. Z goes to Z plus 2 pi and Z goes to Z plus 2 pi tau. Okay, good. Notice that with this, so for instance, if you want a rectangular torus,
Tau has to be pure imaginary.
tau has to be pure imaginary, and its magnitude gives you the ratio of the identification of this size. Size, you know, its length tells you how skewed the torus is, how asymmetric the torus is in identification lengths between horizontal and vertical. Okay? Now, but tau is a complex number which allows you to make an identification like this. Now, modular invariance is simply the statement that if you try to compute a partition function of a theory, if you try to compute the partition function of a theory on such a torus, the answer should just depend on the geometrical shape of the torus. And geometrical shape up to overall scaling, because we're dealing with a conformal field theory. Okay? So there are two so the condition that our partition function only cares about what? Geometrical torus. Sorry, maybe I'm being scattered here. Is it clear what we're doing is now considering quantum field theory on a Euclidean manifold. We were two-dimensional quantum field theory. We're studying it on a Euclidean manifold. That Euclidean manifold is chosen to be a torus. Okay? That torus has, the metric on the torus is unit metric, eta or delta, but it is subject to these identifications. Is this clear? Just to be totally clear. Okay? Now, if I take a well-defined quantum field theory and I put it on a torus, I get an answer. Of course, my answer doesn't depend on how I choose to make this torus. So any two identifications here that in the end lead to the same torus or same torus up to overall scaling have to give me the same answer for my partition function. Okay? Now what are the identifications here that will give me the same torus? Well, there's one obvious thing. Just take tau goes to tau plus 1. What is that? Suppose my original torus was this. Tau goes to tau plus 1 is, so this was the identification with 2 pi, that I keep. This was the identification with tau, but with tau plus 1, it's one factor additional of this identification. So it's saying that this and this is the identification, but it generates the same lattice. So it's the same torus. Do you see? Tau goes to tau plus 1 geometrically gives you the same shape. It's just a different way of thinking in your mind of that same shape. Is this clear? So one subpart of modular invariance is very simple. The condition that the partition function depend only on the geometrical shape on which you're studying it, rather than how you're describing the geometrical shape. One part of that condition is simply the condition that this be invariant under tau goes to tau plus 1. Is this clear? Now there's a second requirement which is a little less trivial. Let's talk about that as well.
In general, it will be invariant under some SL2Z.
Correct. It will be invariant under SL2Z, and we'll see why. Yeah, at the moment I'm preserving orientation.
So tau, ignoring that last argument, would be like the upper half of the complex plane, not the real line, and nothing below it.
Say that again.
For now, the space of possible tau would be the upper half of the
Yes,
complex
yes.
plane, not the real line and nothing below it.
Nothing below it. And
Now we've taken out additionally.
we've taken out.
We've sort of said just make a strip of between the real line and then one above it.
Exactly. And now we're going to take out more things as well. Okay. Okay. So what we're going to do now is the condition that this theory be well defined on a intuitively what I want to do is this. Suppose I reorient my axes. So I think of this as my x-axis. So I just rotate this torus down here. Okay, so first step, I just do this rotation. Okay? So now this identification has gone along the real direction in Z. Okay? Next step, however, it's the real direction but with some magnitude, right? With basically 2 pi times mod of tau. Next step, I divide, I take my whole, I take every coordinate and rescale it. Z goes to Z by mod tau. That changes the metric by an overall constant factor. But conformal field theories don't care about overall constant factors, so it does nothing. Okay? So that then gives me another torus, and this time now in standard form. In standard form with this identification here as 1. And then this gives some new tau here. Okay? And yeah, tau goes to 1 over tau minus 1 over tau. Yeah, tau goes to minus. If you work this out, this turns into the transformation. Tau goes to minus 1 by tau. Okay, and then if you combine these two transformations, you can generate the full set of transformation. Tau goes to a tau plus b over c tau plus d, where a, b, c, and d are integers, and a, b, c, d determinant of. Yeah.
What's the claim that we're making, that tau doing anything of this sort of transformation gives you back the original torus?
Exactly, exactly. That any transformation of this sort can be generated by repeatedly applying these two moves.
Rotate, rescale, rotate, rescale.
Tau goes to tau plus 1, and this rotation. Yes, this is a simple thing to check. I won't try to check it here, but by putting an arbitrary number of this and that, you can get any transformation of this. Okay? So, demanding that your partition function is not a function, not an arbitrary function of tau, but a function that is invariant under this redefinition of tau. Okay? At the level of physics is an obvious demand.
Maybe it does PSL2.
Well, PSL2 is just the statement that if you change all of these, then nothing changes.
It does the PSL2.
What?
This SNT moves generate PSL2.
S and T moves generate PSL2. Sure. I mean, something in which you choose all of these to be minus 1 is just not doing anything, right? Right. So, what am I saying? If you choose minus 1 and minus 1, what?
PSL2 is not about multiplying them all by minus. You would just want, let's say, the A and the C go to minus A and C.
A and D, right? Probably.
No,
You
no.
change sign of all the
I think the full 4. All the 4 have to
all the
change.
4 if you change, then tau does not change at all.
Yeah, unchanged.
Yeah. Now the simplest such element would be to change a by -1 and d by -1. Because that would be
Yeah.
a is equal to -1 and d is equal to -1.
Yeah.
Because that is tau goes to tau. It's a non-trivial matrix, right? It's -1, -1.
Oh, others used to 0.
What? Others 0. It's a non-trivial matrix. It has determinant equal to 1. Okay? But it doesn't do anything to tau. So at the level of matrices, it's a different matrix. Okay? However, on the action in tau, it doesn't do anything. So you should mod out by this action. Modding out by this will be removing your signs, right? Okay. Okay. Yeah. Absolutely.
So just on the A and D sector.
Meaning just things that differ by multiplication by -1 are the same. Right, once I've got a tau, I can do by further transform it by the matrix -1.
No.
That
So the proper group is the quotient of SL2 Z over Z2 times Z2 or just Z2? Just
this is the identification.
Z2. It can make a difference when we take the S matrix of a conformal field theory.
Mm-hmm.
That will have, you can, this implements the S transformation on the characters. And then you can ask that what properties this S matrix has in an arbitrary conformal field theory. And then if it is a representation of PSL2G or SL2, will be important. I'm sorry about this.
Yeah. I'm just saying that the P business is some obvious thing because it just doesn't act on it. Yeah. Okay. Fine. Yeah, right. You can do any SL2Z transformation. Half of them don't act. Okay. 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 Fine. Okay. So let's move. So the question that we're asking is this free boson conformal field theory? Is its partition function? Okay, is the partition function modular invariant? So the first question that we wanted to ask, well, it will be modular invariant if it's invariant under tau goes to tau plus 1, and if it's invariant under tau goes to -1 by tau, because these two generate everything. Okay, so these are the two things we have to check separately. The easier one is tau goes to tau plus 1, so let's check that immediately. So under tau goes to tau plus 1, let's see how the partition function changes. So what we get under tau goes to tau plus 1, this thing transforms like, it picks up trace of q to the pi L naught, q bar to the pi L naught bar. And now tau goes to tau plus 1, so that's 2 pi I I've just shifted tau by 1 and therefore tau bar by 1. Okay. So you see, what's going on here is the following. If every state in the theory, okay, if every state in the theory has L0 minus L0 bar to be an integer, okay, if every state in the theory has L0 minus L0 bar equal to an integer, then this thing is going to be invariant. And basically that will be the only way that it's going to be invariant. Because states with different L0s and different L0 bars will contribute differently in the QQ bar expansion. But each of these terms has to be invariant.
Same statement as this OP does not have this.
Slightly, yeah. It's very similar statement. It may even be stronger. But hang on, it's stronger, it's a little stronger.
At least it implies that.
It implies that. Yes. Okay. So, this condition that L0 minus L0 bar belongs to Z is another condition on the spectrum in order for something good to happen, namely that the partition function be a modular invariant. Now let's check this condition. Okay? What was L0? L0 was L0 was alpha prime, you know, alpha prime by 2 into alpha prime by 4 into k, sorry, what was it? Alpha prime kl squared by 4. Is that right? So L0 was this and L0 bar was that. So I call it P. This quantity has to belong to Z. Okay. Now this is a condition that is, as Indranil said, very reminiscent of the condition we had here. There's one difference though. This is the condition not on pairs of vectors, but on a particular vector. Okay? Let's first check this condition. Let's check this condition and then we'll see how this condition implies the earlier condition. Okay. To check this condition, we need the formula for
No, this condition is a stronger one, right? Because this is for any vectors, for any pair and 2, then it's true for 1 equal to 2.
Yeah.
well, let's apply it to 1 equals 2.
Right, then you get this one.
No, no, you get that, but there's a 4. Here it's a 2.
Oh.
Yes. Okay. So hang on. Yeah. Somebody needs to help me with my PL and PR. What was it? N divided by R plus minus WR by alpha prime. Okay. So once again you've got, you know, this L squared minus R squared. Once again these and these cancel. Once again you're going to get
We'll get a 4 from there.
this time we really get a 4. Okay. Alpha prime cancels and we get NW, which is an integer. So we're all very happy. Okay. Now, I'm going to ask firstly what this condition says abstractly. I'm going to ask what are the words associated with this condition abstractly. Second question I'm going to ask is whether this implies the earlier thing. The words associated with this condition abstractly are simply that the square of any element, this was the norm, right, is an even integer. Okay? So we've seen that the dot product of any lattice vector with any other lattice vector is an integer. Now we've got a new condition. The dot product of a lattice vector with itself has to be even, right? An even integer. Now, why does this imply that? This implies that because of a standard maneuver.
I mean, this is the argument you look for, but this is basically saying that you can use this to build a norm, right?
What?
No, never mind.
Okay. Suppose I have two different lattice vectors, P1 and P2. Okay? I know that P1 plus P2, the whole thing squared is even, belongs to 2Z. But I also know that P1 squared belongs to 2Z and P2 squared belongs to 2Z. And therefore, the difference of all of these also belongs to 2Z.
P1 dot P2 belongs to 2Z. Belongs to Z.
Therefore, 2p1 dot p2 belongs to 2z,
Yes.
and therefore p1 dot p2 belongs to z. p1 dot p2 is an integer. Okay, which is what we had there. So the condition that our lattice was even, that's the term used by lattice people. If a dot product of any lattice vector with itself is always an even number, the lattice is said to be even. The condition that the lattice is even implies that the lattice lies within its dual.
But the other way is
It could be that the other way is also true.
but even here, if we just put
Probably
P1
not.
equals P2, it's not true. Just from this.
Yeah, from this it's not. Yeah, 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 yeah. I think it's not true because otherwise, yeah,
Yeah, I mean, just from this example.
yeah. So far we've got the condition that this lattice must lie within its dual and must be even. Now there is an additional condition that it's actually self-dual. And this additional condition comes from the requirement that the partition function is modular invariant and the tau goes to -1/2. Okay, since we've started this, let's quickly check that this is true firstly mundanely, and then we'll say it more abstractly. Okay, so let's go back to our our periodically identified scalar and compute its partition function. Okay, we can do this from the cylinder picture. Okay, we can do this from the cylinder picture. How do we do that? Well, we had these W winding sectors. In each W winding sector, we had our own spectrum. So the partition function is just sum over W times the partition function, or
N.
yeah, ZW.
Yeah.
Where ZW is the partition function in the Wth sector. Now, what is ZW? ZW, remember, had a part that cared about W and a part that didn't. The part that cared about W was the part that was x is equal to W sigma R, and the part that didn't care about W is everything else. Right? This was that basic maneuver that we take a solution and add something to it that then is universal.
Is it going to be overall factor?
Exactly. That this overall fact, exactly. Now let's compute the energy associated with that let's compute the energy associated, well, okay. Maybe it's just best to do it this way. You see, the energy associated with our with a state is e to the power, the L0 associated with it is e to the power is PL, we've just seen this, PL squared alpha prime by 4 PL squared. I'm putting together, just to save time, I'm putting together the part from the winding and the momentum together. And I'm doing it because then this way I can very simply separate out the Q and Q bar dependencies. Because this contributes to L0 and the other contributes to L0 bar. Okay, L0 bar is equal to alpha prime PR squared by 4. Okay, so our partition function is going to be sum over n and omega q to the power alpha prime by 4 PL squared q bar to the power alpha prime by 4 PR squared times whatever we get from oscillators.
There's a vacuum has this seat.
What? Yes.
I was thinking about
Yes. And it's true that there is also the 0 point energy. The 0 point energy will be q bar to the power 1 by 24, I suppose. We'll just include, since this is universal, we'll include it in the oscillator part. Okay. So the oscillator part will be, okay, let's put it. So there's the q bar. Now this, but we should just get the signs right. It's, yeah, it is q to the power L naught. Yeah, so it's minus 1 by 24. And then the rest of the oscillator part is easy. The rest of the oscillator part is product n is equal to 1 to infinity. Every oscillator, so the oscillators have 1 over 1 minus 1 qn, 1 minus q bar n. Right? Because this is the oscillator, n equals 1 is the oscillator del x, n bar equals, q bar is equal to 1 is the oscillator del bar x. Then there's del squared x, del bar squared x. Each of these is bosonic. That's why they go down in the denominator.
So what happens to this R going to alpha prime by R?
It's okay. Let's take a quick diversion to address that. Actually, it's very clear. Remember that PL was equal to n by R.
Because of that, because N and W gets exchanged.
Yeah.
Minus and some.
That's okay. In the spectrum, it doesn't show up because spectrum has only PL squared and PR squared.
Spectrum will not see this change at all.
Will not say this is this change at all. And this is WR by alpha prime. And PR is equal to n by R minus WR divided by alpha prime. Now, Indranil wants to make the observation that if R is set equal to alpha prime by R prime, there are two radii, one R prime, such that the product is alpha prime. And we rewrite this formula in terms of R prime. Then the formula becomes, let's look at this. Yes. PL is equal to n alpha prime by R prime plus W by R prime. What?
In the second term, the R, it's a WR. It's not WR.
Oh, sorry. This is.
So the R should be up one and down.
Yeah, it's here. R prime by alpha prime. Thank you. And PR is equal to n R prime over alpha prime minus W by R prime. Now, if we also n and R were were dummy variables. Okay, so if we just relabel them, we call this W and this n, this W and this n, interchange n and R. Then you see PL has gone back to PL, but PR has gone to minus a PR. This is actually a sign of a more general symmetry, a more general fact that the free boson theory is invariant under XL goes to XL, XR goes to minus XR. Okay, and this symmetry is called T-duality. And this is a symmetry, under R goes to alpha prime by R prime. XL and XR get interchanged in this way. It's a fact about string theory that string theory in a circle of radius r is the same as string theory in a radius of circle alpha prime by r. And this underlies that. But I won't go into a detailed discussion of that now, because it'll take us too far. Okay.
It also swaps different kind of momentum, right? In other words,
It interchanges momentum and winding.
the spinning and right.
Right.
But is that basically saying, in some sense, the amount of energy contained in each, as long as you swap the radius for one over, for it to get around this way or to go around this way?
Exactly. Let's say that physically.
The same amount.
Let's say that physically. You see, when you've got a very small circle, Kaluza-Klein momenta are very high. Okay? So in particle theory, there's a huge difference between having a big circle and a small circle. Because if you've got a big circle, it's almost like not having a circle. You've got a continuum of states, almost a continuum, a very close discretum of states from Kaluza-Klein moment. You've got a very small circle, the states, a huge gap. But in string theory, you also have winding. And winding behaves exactly the other way. If you've got a small circle, winding it costs almost no energy. So you get a discretum of states associated with winding. But if you've got a huge circle, winding it costs a lot of energy. So there's a huge gap between states. So for this reason, if a very big circle, the winding modes of a very big circle behave exactly like the momentum modes of a very small circle. And there's a precise version of that statement. This is how T-duality works. Okay? But let's get back to that when we get to it. Okay. So we were looking at this partition function. Now I want to check whether this partition function is modular invariant or not. Okay? I want to check whether this partition function is modular invariant or not. Now let's see. You see, how are we going to check that? The first thing we know is that the partition function would have been modular invariant if this quantity here had just been a continuum. If we'd been doing uncompactified free boson. Uncompactified free boson differs. Yes, exactly. This part is the same. Okay? So it differs from. How do I know it's modular invariant? Because a free boson is a modular invariant theory.
No, this is
okay. I mean.
I've never seen a very simple proof of this, so this is
What? I mean, from physics it's totally obvious. And from mathematics it's some function of these, property of these eta functions, right? Okay.
Are we hunting for an anomaly here? Because if the base manifold that we're working on is conformally invariant, then clearly the classical theory is conformally invariant. And now we're sort of asking if this gets lost, if there's an anomaly that makes it gets lost before we get to the quantum side. If conformal will give you modular. Right?
Will give you modular invariance, yes.
Are we just looking for if there's an anomaly here?
Yeah, you see, were you to write down an honest path integral, okay, if we were to write down an honest path integral, you know, we've studied when path integrals for conformal field theories, how they transform under wild transformations. We know exactly how it works. Okay? So were we to just write down an honest path integral, it's guaranteed to work. That's what I meant by from physics, it's obvious. However, what we're trying to do is to go along the lines you suggested. You see, for arbitrary lattice identifications, we don't know if we have an honest path integral. You know, we had an honest path integral when PL was PR, and maybe for some other lattices. But now what we're doing is enlarging the rules of the game and constraining that from symmetries, you know, from consistency. Okay? So we want to have only those modifications of the rules of the game that would give us whatever we should get if we started from an honest path integral. Of course, in the end, all of them will be generated by honest path integrals, but we didn't know that to start with. Okay? It's useful to think this way because it's sometimes these ways of arguing sometimes generalize, where the path integrals don't obviously generalize. Is this clear, what we're trying?
But we're still definitely on the torus, right?
We're on a torus, but we've taken the structure of the theory and molded it a bit. We've just declared by hand.
I know, but conformal invariance is not a statement about your theory. Conformal invariance is a space-time symmetry. Is a space-time transformation. So it almost seems like it shouldn't matter what you're doing to your theory. But if your space has a property, if your space is periodic, your theory is periodic, right?
Well, if the path integral on that works, provided you can define the path the partition function by a well-defined structure on that space.
And this is what we're not sure about.
This is what we're not sure about. For instance, in a theory where CL is not equal to CR. Do you remember last semester we saw there was a diffeomorphism anomaly?
Yeah.
So the path integral on a space is not well defined.
Right.
There it will depend on what way you represent the space. That's an example from our point of view, our current point of view, of an illegal theory. Okay? If we have a structure that depends just on the geometrical shape, a diffeomorphism invariant path integral, then what you say is completely right. We're checking whether our mauling of structures preserves this property.
So this is like a consistency check.
Yes. A consistency check, but yeah. Of a set of rules.
Right.
Yeah. Okay. Of course, for the particular case of a single free boson on a circle, we're pretty sure we land on our feet because we did it very clearly. But we're going to very fast generalize this to more broad situations. And this way of thinking will help us. Okay. So let's continue. Suppose we took this oscillator part and added to it the part that came from just the continuum. Okay? We added to it the part that came just from the continuum. That part is definitely going to be modular invariant. You can check it from mathematics also. Okay, it's going to be modular invariant. So what is the path that would have come from continuum? Well, the path that would have come from continuum, in that case we would have had q bar to the power alpha prime p squared by 4. Because pl squared is equal to pr squared. Okay? And then we would have had dp by 2 pi times the length of the space. Okay? So now this is the same as dp by 2 pi times e to the power minus alpha prime by 4 into minus log q bar into p square. Okay, we could say this all in more physical terms. Well, okay, let's say it like this, and then we say it more physically. Okay, but then this is a Gaussian integral. Okay, so this gives a factor of 1 over square root of whatever comes behind here. Okay, so and there's some 2 pi's and so on, which I'm not keeping track of.
But that's not necessarily, positive, right? The Gaussian integral,
yeah.
It's not, the analytic continuation does not work for some.
No, but it is positive because actually, we were looking at.
Q bar.
Yeah.
The log q bar has to be negative then.
Yeah, we'll only compute trace of this with tau having positive imaginary part. Tau will be equal to tau 1 plus I tau 2 greater than 0. Right, because we want to compute a well-defined partition function. Because this is the Euclidean time direction, and we want to get trace e to the power minus beta h, not e to the power plus beta h. That was That would have been a danger otherwise. Okay. So let's check that if we're doing this. Okay, sorry. Okay, we're going very slow in today's class, but it's okay. Let's go back to our definitions and check that if this is working, everything will be okay. What did we have? We had e to the power 2 pi I tau, which was q, times L0 times 2 pi I tau bar times L0 bar. We don't care about the phases, we care about the absolute part, so we care only about the imaginary part of tau. Okay, so we will get e to the power minus 2 pi I tau 2 times L0 plus L0 bar. Okay, this is the Hamiltonian. So we're only going to compute partition functions where tau 2 is positive. Okay, otherwise, of course, we're looking at a quantity that didn't make sense.
The I wouldn't be there.
Sorry, you're right. I said that. Okay, so we're going to restrict attention to those things such that tau 2 is positive. Now let's compute what log QQ bar is. Yeah, exactly. So log QQ bar was e to the power 2 pi log of e to the power 2 pi I tau minus tau bar. Okay, so tau minus tau bar, the tau 1s cancel. The tau 2s become I tau 2 minus I tau 2. So e to the power 4 pi minus 4 pi tau 2. So this log is negative. That's why I put the minus sign. Okay. Okay, so now if we compute this, this p integral, what will we get? We'll get a factor of 1 by square root of minus log q bar. Wait, but log of this up to some 2 pi's and so on is tau 2. So maybe it's better to write this as 1 by square root of tau 2.
Yes.
Okay. So this quantity here, so let's say the partition function is equal to sum times oscillator piece. We know that oscillator piece by square root of tau 2 is modular invariant. Okay, so if we just multiply square root tau 2 by square root of tau 2, then our partition function is going to be modular invariant if and only if this sum here times square root of tau 2 is modular invariant. Is this clear? Another way of saying it is just that the sum should have the same modular transformation property as the part of the partition function that came from the zero mode continuum in the free theory.
Then again you will use Poisson summation.
Exactly. Okay, so we've got sum over the lattice e to the power minus PL squared by 4 alpha prime PL squared by 4 Q to the power. Q bar to the power alpha prime PR squared by 4 square root tau 2. We want to check whether this quantity is modular invariant or not. Is it modular invariant? That's the question. Okay? Now, how do we check such a question? Well, first let's do it completely explicitly, and then I'll give you the abstract, the more abstract description. Completely explicitly, I'm just going to write this out. Okay, so for the completely explicit thing, what we're going to do is just completely write it out. So what do I have? I have e to the power 2 pi I tau into alpha prime by 4 into n by r plus w r alpha prime squared times e to the power 2 pi minus 2 pi I tau bar alpha prime by 4 n by r minus w r by alpha prime, the whole thing square. And then we have to do the sum of times tau 2, sum over n and w. Okay. Now what we want to do is the following. What we want to do is to use this lovely formula. Okay, this lovely formula which we have to get straight with the 2 pi's, but not being very careful, we have the following statement. Suppose I have a function f of x, and I have its Fourier transform. Okay. So I have a function f of x, and f of x is equal to e to the pi kx f tilde of k. Okay, we need to get various things carefully. Okay. Okay. Then there is this statement that sum over n f of n, sum over n of f, and maybe there is some. Yeah. Person. Somebody's there. Yeah. What?
I think the square.
No.
Okay.
No.
Okay.
It's the sum of
I see.
f is the sum of. This may be at evaluated at 2 pi n. I'm going to get all that straight. Or maybe I'll leave. Maybe we'll get it straight next class. But where this guy was the Fourier transform of this. So if you've got a function that you're summing over all integer values, you may as well sum instead the Fourier transform of that function over all integer values. Now what we're going to do is the following. Now what we're going to do is to use this formula to try to prove that this function really is modular invariant under tau goes to minus 1 by tau. Okay? And the basic point is going to be this.
Standard deviation in Fourier transformation is 1 by, it changes.
Exactly. The basic point is going to be this, that if you've got a tau multiplying a Gaussian, then its Fourier transform is multiplied with 1 by tau. If you've got e to the power ax squared by it, then the Fourier transform of that is e to the power k squared by a. This is what's going to accomplish the tau goes to 1 by tau. There are eyes, you have to do all kinds of things, but okay, you have to do it carefully. Also, we wanted it to be Fourier, thing along with the square root tau. But let us remember
That the normalized.
that the Fourier transform of a Gaussian is not quite a Gaussian.
1 by root tau.
It comes with a determinant factor. Okay, and that determinant factor will account for this 1 by square root tau. Now I think we're going to have to stop today because I have to go home to come for your terrace party. Okay. Yeah. Anyway, it's been 2 hours. Yeah. So I'm going to leave this as an exercise for you guys. But I had to give you an exercise for today also. Did anyone try? I can't even remember what the exercise was. But,
Sum over n minus.
what? You had to evaluate the vacuum, the energy in those modules, in those sectors. Did anyone try it? Did you try it? No? I'll tell you what, for the registered students, what we will do is assign exercises. Okay? Are you registered, Amio? Are you registered for the course? No. Okay, see, listen, so you two guys are the 2 registered students at the moment. So you choose one of these 2 exercises. One of you show me the modular invariance of this quantity using Poisson resummation, and one of you show me that the energy matches in the other sector. Okay? And maybe at the beginning of next class we can have 5 minutes from each of you on these things. Okay? Okay? This way I can, then we don't need to have evaluation at the end. Okay? So I'm sorry this class went much slower than I had thought. We got a little bit willied with questions. I'll tell you where we're going though. I'm sorry it's taken so long, but I'll tell you where we're going. I hadn't intended to get into so much detail about this, but anyway, I wanted to show you that this that there is a particular compactification radius for the free boson in which it becomes exactly the free fermion theory. Free fermion theory, but with both left moving and right moving free fermions, complex left moving and complex right moving fermions, and with a particular choice of sectors for the free fermion theory.
Would it be the square root alpha? No, square root alpha prime? No, right?
Yeah, it is.
Because fermion theory does not have this kind of dualities.
Exactly.
It must be the self-dual.
Another way of saying it is that we know that there are operators in the fermion theory which is only right moving or only left moving.
Yes.
On the other hand, our PLPR was n by r plus WR by alpha prime and n by r minus WR by alpha prime. At an arbitrary radius r, there is no choice for n and w for which you have only PL but no PR. Which means there are no purely left moving or purely right moving operators. Okay? But suppose R was equal to alpha prime by R.
Square root, yeah. R is square root.
Yeah, suppose these factors were the same, then you could take them out. Then of course there are operators in which this works. Okay? So that's the place where it's going to, where it's going to work. That's mainly what I wanted to show you today's class. We didn't get there. I'll quickly show that to you next class, and then we move on to our fermionization for the beta gamma system, which is really, where we want to go. Okay.